Well, equilibrium constants, as we've said, are the holy grail of equilibrium reactions and the analysis of them, because the reaction after the stress is applied always comes back to the same equilibrium point. So this term equilibrium constant is, it turns out, invariant with increasing pressure, decreasing volume, increasing concentrations. But now we want to look at the impact of temperature. So the applied stress is then, in examples we'll look at, increasing temperature superimposed on a system that's currently in equilibrium. So when we look at this term equilibrium constants, which we've used repeatedly, we have to be aware that in general these equilibrium constants are very sensitive to temperature. And when we study kinetics, we'll learn a fundamental point, and that is, with increasing temperature, the reaction with a larger barrier increases more than the reaction with the lower barrier. So what does that mean in general? If we take arbitrary reaction between A and B going to products G and H, we know that we can calculate the enthalpy release in the reaction, and in this case, when we proceed from A plus B to G plus H, we actually release chemical energy in that process. But if we're looking at an equilibrium, the reaction from products back to reactants has to climb a higher barrier than does the reaction going in the forward direction. And that means that the reaction going in the reverse direction speeds up more with increasing temperature than does the reaction carrying reactants to products. So let's take a very specific case in point. Let's take the case of analyzing the response of NO2 to form the dimer N2O4. And as we pointed out before, this reaction is very important in urban environments because the NO2 molecule forms the N2O4 molecule, also in the gas phase. And the NO2 molecule is orange in color, and the N2O4 molecule is clear. It doesn't interact with electromagnetic radiation within the range of the human eye. And so the orange color that you see over cities in the summer reflects the presence of NO2, but if we are going to increase the temperature, we want to know what the effect will be on the relationship between the concentrations of NO2 and the concentration of N2O4. So we know from our previous analysis that if we are converting from N2O4 back to NO2, that has a higher barrier than the reaction of NO2 forming N2O4. So we can write this then as a reaction of NO2 with itself forming N2O4, and these are all in the gas phase. But we notice also that the enthalpy release means that we're producing heat on the right-hand side of that equation. So now let's investigate. Let's take NO2 at room temperature, and we know that the NO2 is in equilibrium with N2O4, and let's suppose we cool that mixture, and we notice that 2NO2 going to N2O4 has shifted to form more N2O4 relative to NO2. So again, the applied stress, let's assume that we're going to increase the temperature in this equilibrium. And if we increase the temperature, that means it's speeding up the reaction in the reverse direction. And that means that we're driving the reaction, in this case, from right to left, and the reaction then means that this reaction will take up heat in order to execute the reaction back from N2O4 to NO2. So if we increase the temperature, that means that the shift from N2O4 to NO2 plus NO2 takes up heat. We're driving it in the endothermic direction, And that means it's trying to cool the system in response to that increasing temperature. So you can see that the response of this chemical equilibrium, again to an external stress, is such as to moderate that stress. And in this case, the increasing temperature means that the system cools because it's endothermic, and delta H is positive as we shift from N2O4 to NO2.